William Foster wiped the grease from his weathered hands as he stared at the mechanical monstrosity taking shape in his Lincoln engineering workshop. At 42 years old, he was one of Britain's most innovative agricultural machinery designers, known throughout England for creating tractors and steam engines that had revolutionized farming. But on this fog-shrouded morning in September 1915, as the Great War raged across Europe's muddy battlefields, William was building something that had never existed before: an armored vehicle that could cross trenches, break through barbed wire, and change warfare forever. The project had begun 6 months earlier when Colonel Ernest Swinton, a British military engineer, had approached William's company with an unusual request. The British Army was desperate for a solution to the deadly stalemate of trench warfare, where thousands of soldiers died daily attempting to cross no man's land against machine gun positions that made conventional infantry attacks suicidal. Swinton believed that an armored, tracked vehicle could break through German defensive lines and restore mobility to battlefield operations. William's background made him uniquely qualified for this revolutionary assignment. Born in rural Lincolnshire, he had learned mechanical engineering through apprenticeship with his father, who manufactured agricultural equipment for local farmers. By 1900, William had established his own workshop specializing in tracked vehicles for agricultural use, creating some of Britain's first successful crawler tractors that could operate effectively in muddy conditions that defeated wheeled vehicles. When war erupted in August 1914, William had initially contributed to the war effort by converting his workshop to produce artillery shells and military vehicles. But Swinton's request presented a completely different challenge: designing an armored fighting vehicle that could survive battlefield conditions while providing mobile firepower against enemy positions. The concept existed nowhere in military doctrine, engineering textbooks, or practical experience. The technical requirements for the vehicle were staggering and seemingly contradictory. It needed to be heavily armored, enough to resist machine gun fire and shell fragments, yet light enough to navigate across soft ground without becoming immobilized. It had to be powerful enough to cross barbed wire and cross trenches up to 8 feet wide, while maintaining mechanical reliability under combat conditions. Most challenging, it needed to carry sufficient armament to suppress enemy defensive positions while protecting a crew capable of operating the vehicle effectively. William began the design process by studying the tactical problems that British forces faced on the Western Front. Machine gun nests positioned in reinforced concrete bunkers could devastate attacking infantry from distances exceeding 1,000 yards, while elaborate trench systems created obstacles that were virtually impossible for conventional military equipment to overcome. Artillery bombardments could destroy specific positions, but they also cratered the ground so severely that follow-up infantry attacks became even more difficult. What would you do if asked to invent something that had never existed to solve an impossible military problem? The initial design concepts William developed were based on his experience with agricultural tracked vehicles, but adapted for military requirements that pushed existing technology to its absolute limits. The vehicle would use caterpillar tracks similar to those on his farming equipment, but reinforced to carry armor plating that could weigh several tons. The engine would be a modified version of the power plants he used for heavy tractors, but adapted to provide the additional power needed for combat operations. The armament posed particularly complex challenges. William needed to mount machine guns and possibly light artillery in positions that would allow effective fire against enemy positions, while ensuring that the weapons could be operated by crew members who were simultaneously managing the vehicle's movement and mechanical systems. The solution required innovative engineering that balanced firepower, protection, and mechanical reliability in ways that had never been attempted. Working 16-hour days in his Lincoln workshop, William began constructing prototype components that would eventually become the world's first operational tank. The tracks were fabricated using techniques adapted from agricultural equipment manufacturing, but reinforced with steel plating that could withstand combat stresses. The armor was constructed from rolled steel plates, bolted to a framework that William designed to distribute weight while providing maximum protection for essential vehicle systems. The engine installation required extensive modifications to adapt automotive power plants for tracked vehicle applications. William selected a Daimler six-cylinder engine that produced 105 horsepower, sufficient to move the heavily armored vehicle at speeds up to 4 miles per hour across rough terrain. The transmission system was entirely his own design, incorporating multiple gear ratios that would allow precise speed control during tactical operations. The vehicle's steering system presented unique challenges that Williams solved through mechanical innovations that would influence tracked vehicle design for decades. Rather than using conventional steering wheels, the tank would be controlled through a system of levers and brakes that could stop one track while the other continued moving, allowing the vehicle to turn in place or navigate around obstacles with precision that would be impossible for wheeled vehicles. As construction progressed through the autumn of 1915, Williams' workshop became the center of intense activity as engineers, military officers, and government officials monitored the development of what everyone understood could be a war-winning technology. The security surrounding the project was extraordinary, with armed guards protecting the workshop and strict orders that all personnel involved in the construction maintain absolute secrecy about their work. The transition from prototype development to mass production presented William with challenges that tested every aspect of his manufacturing expertise. His workshop facilities had to be expanded dramatically to accommodate tank production, while his workforce grew from 12 employees to over 500 workers trained in specialized manufacturing techniques required for armored vehicle construction. Quality control became critical as Williams' tanks entered production, since mechanical failures in combat could result in crew deaths and mission failures that might influence the entire course of the war. Every component had to meet specifications that ensured reliable operation under conditions that would destroy conventional machinery, requiring inspection procedures and testing protocols that William developed specifically for military applications. The first production tanks were completed in August 1916, just in time for their combat debut during the Battle of Flers-Courcelette in September. William accompanied the first tanks to France, not as a combatant, but as a technical advisor responsible for training British crews and maintaining the vehicles under battlefield conditions that would test every aspect of his design. Let us know in the comments what you think about seeing your invention used in actual combat. The combat debut of Williams' tanks was both triumphant and sobering, demonstrating the vehicle's revolutionary capabilities while also revealing limitations that could only be discovered through actual battlefield experience. Of the 49 tanks deployed during the September 1916 attack, 17 broke down due to mechanical problems, 5 became stuck in shell craters, and 9 suffered combat damage that disabled them before reaching their objectives. But the 18 tanks that successfully completed their missions achieved results that exceeded the most optimistic predictions of military planners. They broke through German defensive lines that had resisted conventional attacks for months, captured strategic positions with minimal casualties, and demonstrated that armored vehicles could indeed restore tactical mobility to battlefield operations. The psychological impact on both British and German forces was enormous, with British troops gaining confidence while German soldiers experienced their first encounters with weapons that seemed invincible. Williams' immediate response to the combat reports was characteristic of his engineering approach. He focused on the mechanical failures and design limitations rather than celebrating the tactical successes. His analysis of tank performance during the battle identified specific improvements in engine reliability, track durability, and armor configuration that could increase battlefield effectiveness while reducing maintenance requirements. The modifications William implemented based on combat experience resulted in improved tank designs that gradually addressed the reliability problems that had limited effectiveness during early operations. His willingness to acknowledge design flaws and implement engineering solutions
demonstrated the iterative approach to innovation that would make British tanks increasingly effective throughout the remainder of the war. By 1918, Williams' company had produced over 2,600 tanks that had fundamentally changed the nature of battlefield operations. The vehicles he had designed in his Lincoln workshop had broken through defensive lines throughout Europe, contributed to major Allied victories, and demonstrated the potential for mechanized warfare that would dominate military thinking for the remainder of the 20th century. The end of the war in November 1918 brought new challenges for William as military demand for tanks disappeared, and he faced the need to convert his expanded facilities back to civilian production. But his wartime experience had established him as one of the world's leading experts in tracked vehicle design, creating opportunities in agricultural and industrial applications that would sustain his company for decades. Williams' personal satisfaction came not from the commercial success of his designs, but from knowing that his engineering innovation had contributed to ending a war that was consuming an entire generation of young men. The tanks he had built in Lincoln helped break the stalemate of trench warfare, allowing military operations that shortened the conflict and saved countless lives on both sides. In 1919, William was knighted by King George V in recognition of his contribution to Allied victory, becoming Sir William Foster and joining the ranks of individuals whose innovative thinking had served their nation during its greatest crisis. But he remained modest about his achievements, understanding that his success had resulted from applying practical engineering skills to military problems rather than developing revolutionary new technologies. William continued developing tracked vehicles throughout the 1920s and 1930s, creating agricultural equipment that revolutionized farming while also contributing to the development of military vehicles that would prove crucial during World War II. His engineering principles and design approaches influenced armored vehicle development for decades, establishing foundations for modern tank design that remain relevant in contemporary military applications. Sir William Foster died in 1946 at age 73, having lived to see his mechanical innovations influence 2 world wars and transform both military and civilian transportation. His obituary in the Times described him as the father of the tank, but those who knew him best understood that his greatest achievement was applying practical engineering skills to serve humanitarian objectives during humanity's darkest hours. The original workshop in Lincoln where William built the world's first tanks has been preserved as a museum, commemorating his contribution to mechanical engineering and military history. Visitors can see the tools and equipment he used to create revolutionary vehicles, along with detailed drawings and photographs documenting the development process that transformed innovative concepts into battlefield realities. Today, Williams' legacy extends far beyond his specific contributions to tank development. His story demonstrates how individual creativity and mechanical expertise can address seemingly impossible challenges when applied with determination and innovative thinking. The tanks he built in 1915 and 1916 established principles of armored vehicle design that continue to influence military engineering throughout the world. Sir William Foster proved that revolutionary changes in warfare could result from practical engineering applied to tactical problems rather than dramatic technological breakthroughs. His achievement reminds us that innovation often emerges from workshops and factories rather than laboratories, and that individuals with specialized skills can make contributions that change the course of human history when their expertise meets critical needs. If you enjoyed this story, please like, subscribe, and leave a comment.